equation modeling, they are tools to infer causality. We are interested here in knowing the cause and effect relationship, the cause and the effect. And this arrow basically indicates the cause and the effect. So in this series, we will be looking at another very classical tool, and that is called covariance based structural equation modeling. Now, this software Smart PLS, as the name indicates, PLS stands for partial least square structural equation modeling. And this partial least square structural equation modeling is a new approach to structural equation modeling as compared to the classical approach of uh, covariance based structural equation modeling. So this partial least squares, it comes from a technique called partial least square, what you call regression. And in this regression example, there was one last discussion that we did was of collinearity. So what happens sometimes in linear regression, there are lots and lots of variables. In real life, for example, you are making big models to predict something in real life like stock prices and everything. They have lots and lots of factors. And sometimes those factors are very closely related with one another, and the theory also justifies them, and you cannot also delete them. Then in case, what we will do? So basically partial least squares regression is, it groups the highly correlated variables into one variable known as a composite or a principal component, and then estimates the value of that principal component and use that value to regress on the dependent variable. So this is how partial least square regression works, and this is the same concept that the partial least square structural equation modeling uses. It now extends this to what you call latent variables, because in latent variables, all the questions inside a scale are highly correlated with one another. That's why you get very high reliability and composite reliability and alpha values. So in order to avoid problem of multicollinearity, it just groups them and calls it a latent variable. Now, covariance-based structural equation modeling uses now this basically this PLS technique for which the Smart PLS software was created. It uses normal least square regression, which we just saw in the previous example. Whereas this CBSEM, covariance-based structural equation modeling, it uses the maximum likelihood estimator to estimate the values of all the path coefficients. So linear regression is a very simple methodology. Maximum likelihood is not. And if you want to read about it, you can just Google maximum likelihood estimators, and you will get a very detailed mathematical description of all these techniques. But since we are only interested in the using of CBSEM as a tool, so we will look at CBSEM as a tool here. Okay, so we will start with CB7 in Smart PLS. We'll just come to the main window, and here you can see in the top, we can select the type of project we want. So we'll just click CBSEM, project CBSEM, model type, CBSEM, give it a name, and just click save. I have already made, so I will not click this. And then we will go to this model, and here we will also import our data. So we will just click here, import data file, and we will go to the place where we have stored the data for this. This is the data file that I have selected for this example. And the same window will appear. Just click import. And this is the, what you say, snapshot of the data file that we just imported. Okay. So now what this data indicates, so you can see there are 32 variables, and there are 397 observation for these variables. Okay. So what is this data about and what model we will testing? Now let us look at it. So this is from another one of my published studies. This model. Okay, this was published in 2019. I co-authored this study. And this is the framework. Is this framework visible? Okay, so this is the framework that we want to test here. And you can see it's a very complicated model as opposed to this simple model of where all the arrows were coming down directly onto one dependent variable. Here you can see that there are two stages. First, these three affect this, and then this effect transmits here, and then there is another independent variable which is coming in directly. So what this study tried to focus is that how implementation of blockchain in supply chain might improve certain supply chain parameters like alignment, agility, and adaptability, which leads to competitive advantage. And naturally, competitive advantage is there that will lead to better fund performance. And trust generated by all these blockchain type technologies will also increase the fund performance. So this was our model, and we wanted to test this model, and we collected the data from industry managers by sending them questionnaires over the email. We have mentioned all this in detail in the methodology section. So these are the questions that were used for measuring all these construct. For example, supply chain agility. These were the sources from which these questions were obtained, and these were the what you call the questions that we use. These are called the indicators. So why we need structural equation modeling? Because you can see that here supply chain agility. This is known. These things are known as latent variables. Okay, latent variables are used where we are measuring abstract concepts. Abstract concept means concepts which we cannot uh, quantify directly. For example, if you want to measure the length of a table, you can quantify the length. Length is a quantifiable quantity. Okay, you can measure in meters, centimeters, okay, millimeters. Whatever you measure in feet, inches, whatever you measure in, the length will be the same. Okay, and it will be same everywhere on planet Earth. Okay, but in case of this abstract concept, for example, how do you think how adaptable you are, what are your weak points, what are your strong points, इस तरीके की जो चीजें होती हैं, these are called abstract concepts, and these cannot be gauged directly. That's why we need to refer to certain indicators, and from those indicators we again infer the value of the underlying construct. Okay, so basically agility is a capability of a supply chain or any other in any manufacturing unit to quickly adapt itself to changing conditions. Okay, and this is basically a skill which is learned by managers through experience and through use of analytics, that how quickly they can gauge and predict what will happen in the future. So this is largely an abstract concept, and a lot or depends on the opinions and the abilities and the experience of the managers involved. So that's why it is measured using a battery of 8 items. Okay, and these are the source from which we have obtained these items. Similarly, supply chain alignment, supply chain adaptability, firm performance also. This is just a perceived impact of firm performance, trust, and lastly, competitive advantage. Okay. So you can see that the questionnaire has all lots of questions, and these are the main constructs. And now we want to test this model. So cases where you have variables which are measured by lots of constructs, constructs or variables which are measured by lots of indicators or items, and you want to test a what you call causal structure like this, structural equation modeling is the most useful tool. Now there are two kinds of structural equation modeling: covariance based and partial least square structural equation modeling. So when to use when? PLSM is used when you are doing exploration and prediction. Okay. For example, we have made this model by reviewing past literature. Okay, so literature is already present, and in theory they have mentioned all these things. We have discussed how these variables relate, and we have formed a theory, and we want to test this theory using field data. When you are testing a theory from field data, then CBSEM is the most important tool. However, if you are doing data exploration and you are trying to see which factor affects which and what are the theory building exercise में हो अभी उस phase में हो, you are trying to see which variable affects, which variable does not affect. Okay, you are trying to shortlist everything. Then in that case, PLSM is very important. PLSM is used in the initial stages, whereas when we try to replicate or we try to fit data to existing theories, then CBSEM is required. And that is why CBSEM has fit indexes, because we are trying to gauge whether the data fits the model and vice versa. So this is the model that we have formed. We have said that supply chain alignment, agility, and adaptability affect competitive advantage. So this is the dependent variable for all these three variables. And then competitive advantage affects firm performance. That means now competitive advantage becomes independent and firm performance becomes the dependent. This is another independent variable which is not related to any of this. It is directly affecting firm performance. And if we see this model, we see that competitive advantage is in the middle. Okay, so it's in the middle. So that means this is also acting as a mediator. Okay, these are the independent, this is the dependent, and this is also a mediator variable. So we will be also checking how to see for these type of indirect effects in CBSEM, because CBSEM does this work all in one, and this reduces your type 1 error. So that's why SEM is the most preferred methodology when you are submitting papers to international journals, and that too if you are testing these type of complex models, then SEM is the only methodology that we apply, because it also validates our questionnaire as well as validates the causal network also. Okay, so as we saw that all these constructs are measured by these items. Okay, and I said that these items are basically trying to measure this abstract concept. So that means SAM involves two analysis. First of all, we'll have to ascertain that all these items can actually predict this supply chain agility or supply chain alignment. That means whether the indicators can predict the latent variable, and secondly, the independent latent variable, how they predict the dependent latent variable. So there are two analyses involved in SAM analysis. Any question up till here?
Sir, you said that for already existing theories, we can adopt this model, and if I want to introduce one more variable into it, which is new to the existing theory, then will this be possible?
Yes, you can do that. Okay. Actually, there is no hard and fast line between PLS and CBSEM. Okay. And this is what I just quoted is from quoted by Higher JF in his book Primer on Partial Least Square Structural Equation Modeling. However, if you look at the publications in Google Scholar regarding PLSM or CBSEM, you will see that CBSEM is going a little out of favor for even theory testing also. Okay, not theory development, but theory testing also. PLSM is taking the stage. Now, that the reason behind is that CBSEM has lots of assumptions when it comes to the data that it is fed into the what you call algorithm, this maximum likelihood algorithm. Data should be normal, data should not be very skewed, and it should be normally distributed, randomly collected, many things. Now, sometimes these types of assumptions get violated in social sciences when the data is collected in the field. And to address this, what these guys did, what they made PLSM non-parametric, and the significance is, as what you said, obtained not by looking at the distribution, by constructing a distribution by doing bootstrapping. So yes, you can use both of these techniques interchangeably. There is no hard and fast rule. As per the convenience of the text, I just quoted Higher JF. But nowadays, even PLSM is also used for what you say theory testing also, because how they test is they see that if the dependent variable is being able to be predicted with high degree of accuracy, then that means the model is already fit. You don't need any special indexes. Whereas in CBSEM, we have indexes like CFI, comparative fit index, RMSEA, P close, everything, all that. So I think, sorry for the deep discussion on this, but I think that clears the doubt on this issue. Any other queries? Any other queries up till here before we jump into the analysis? Okay. Now let us take the analysis forward. So as you can see that all these variables in our study, these are latent variables which are measured by these indicators in the questionnaire. And first of all, we have to see whether these indicators are a valid and reliable method of predicting these in underlying construct, and then we will see whether the underlying construct predict our dependent variable. So there is a two-step analysis involved in CVSEM. So the first step.
So one more thing I just want to understand that you showed this,
Yeah.
and here, can you go down? So
Yeah. Towards the table, yes.
yeah.
Okay, okay.
See here, you have given sources of the items and the question, and then standard factor loading.
Uh-huh.
So this loading is already being taken from the existing analysis, or we have taken our own.
No, no, no. This is not taken from the existing analysis. This is our own reported loadings. That's why I didn't discuss it, because we will
Yeah.
be discussing it when we run the first stage of the model. Okay.
Right, right. Okay.
Okay, these are the studies from which we have adopted. Basically, if you want to capture any abstract concept, let us say like supply chain agility, that how flexible is the mind of the supply chain manager or the operation manager who is sitting at the top forming strategies for the supply chain of your company. What we did is you have to know what are the characteristics of the underlying concept. And we referred to all these studies and we found these characteristics which are very, repeatable, and they were very common. So we just made them into questions, anchored them on a 5-point Likert scale, and just did our survey with the managers. Okay. So now
Fine.
we have to first of all validate whether the characteristics that we have taken and the response that managers have given, that they actually represent supply chain agility or not. Okay. This is the main task. This is the first task. That is validating the constructs or validating the questionnaire. In simple terms, we say this: validating the questionnaire. And after you validate the questionnaire, then you test the theory that whether the independent variable affects the dependent variable or not. Okay. So if we then open this with our spreadsheet app, Excel, then you can see that this is how the data for this paper was organized. So this is supply chain adaptability, 4 items, supply chain agility, 8 items. Similarly, firm performance, trust, competitive advantage is measured by 3 items, and these are the individual responses of the managers which they filled the questionnaire. So every item is anchored on 5-point Likert scale. Okay, so this is how these guys, they submitted their responses, and after that we just brought that file into Smart PLS, and Smart PLS is giving it the mean, median, minimum, maximum, and the kurtosis and skewness of these values. These are also within the limits. Okay, and standard deviation. Standard deviation should not be greater than plus minus 1, ideally, but it can go, but it should not be more than, it should not be very a big number. It should be as small as possible. That means key there is no outliers in the data. The data is very much uh, conforming to a very normal type of a distribution. This is how we diagnose problems in this, data import window. When you import the data, this is not just for, verifying that data is read correctly, but this is also, to diagnose problems very early on. If the skewness or kurtosis or standard deviation, if all these values are, trying to hunt in what you say directions which are beyond acceptable, then that means some assumption has been violated, and this will cause problems later in the model. So better is that we see the problems here and try to rectify them before they become bigger problems and they become, pretty much insoluble when the model is, run. So we have just imported our data. Now we'll just go click back and go to the canvas. Okay. Now in the canvas, we will have to draw this model as it is, so that the relationships that we are trying to test, they are same, not different. We'll just go to this here. We'll have to draw this model as it is and supply all the indicators. So we'll just go to the canvas and let us first of all select firm performance, FP, because this is our dependent variable. We'll just select all these and just click and drag here. Let us call this firm performance. So you can see it has created a latent variable this. These are all the indicators or the questions on which we have taken responses from the managers on a scale of 1 to 5. These are known as the error terms because, as I said, first of all, we are trying to test whether all these indicators can predict this underlying, what you say, abstract concept, concept or construct or the latent variable. So these are the error terms associated with each of these indicators. Similarly, we will just add every other variable. We'll call this supply chain alignment. Then we have 8 items for agility. We have 8 items for agility. Then we have adaptability. And we have then trust. Let us call this trust. And we have competitive advantage. Okay. So now let us first ensure from the text that all our variables are there. So we have supply chain alignment, adaptability, agility, competitive advantage, firm performance, and trust. So, as I said, it's a two-step analysis. First of all, we'll have to see whether all these indicators they are actually measuring the underlying construct correctly or not in a reliable and valid way. Now, this stage of structural equation modeling is known as confirmatory factor analysis. Okay. So how do we run this? First of all, confirmatory factor analysis. We'll just load all our, what you say, independent variables or any variable dependent, independent, all variables. Okay. Dependent variable here are two, competitive advantage and firm performance. These are our independent variables. We load all of them in the canvas. And then what we do is we click select. We just select all of them. Okay. As you see, there are 6 variables. We have selected all the 6 latent variables and we just correlate them. Correlate them in such a way that every variable gets correlated with one another perfectly. Okay, there is no path left. You have to draw this, what is known as correlation. Okay, this will also help us to, ascertain whether there is any multicollinearity or discriminant invalidity type of issue. Now, when we have done all this, we have drawn all the correlations. Alignment to competitive advantage, firm performance, trust to here, adaptability to agility. Okay, no path is missing here. We have drawn all the correlations and now we will go to calculate. And we will select here basic CB-SEM algorithm. Do not change any setting here. Okay, leave everything as it is. I have actually changed the setting for some previous analysis. Don't do that. Don't change any special assumption settings here. Leave everything as it is. Okay, iteration count at 1000 and just click start calculation. Okay. Okay, now it is done and we can see that Smart PLS has reported some values on these arrows, some values on these arrows, and some values in these circles also. So let us see what are these values, what is their meaning, what does these values convey in relation to our analysis in the first phase of this analysis known as confirmatory factor analysis for validating the questionnaire and the scales used. Okay. So first of all, when we are running CBSEM and that too confirmatory factor analysis, first of all, we'll have to go to this quality criteria and select model fit. Okay. Before interpreting any CBSEM model, we'll have to, look at the model fit. And if the model fit is within these acceptable criteria, then only we go to interpret the model, else we drop the model. Because CBSEM is largely entrusted with the responsibility of saying whether theory matches the data or not. Okay, so for that, these fit indexes are very important. So as you can see, a lot of fit indexes, lot of numbers, abbreviated fit indexes. Name of these fit indexes is shown here. Okay, these are abbreviations. I'll explain all these abbreviations, and their values are estimated model. They have been what you say estimated here. So usually nowadays, journals require you to report two important fit indexes in your paper. First is this CFI. Okay, CFI stands for Comparative Fit Index, and lastly this RMSEA, root mean square error of estimation. Okay, these two indexes nowadays are being reported. Earlier, this TLI, GFI, AGFI, PGFI, all these were being reported, and these have to be at least zero point 0.9 in order for a good fitting model. Nowadays, only CFI and RMSE are required. Why? Because it was reported some time back that these two fit indexes are least affected by sample sizes. Okay, that means you cannot manipulate these indexes by increasing or decreasing the sample size. That's why these two indexes now are finally being called upon when fit indexes are being reported for CVSAM. So what is this CFI? CFI is comparative fit index. Now for a good fitting model or an acceptable model, CBSEM model, the value of CFI should be greater than zero point 0.9. Okay. So here for our measurement model or our confirmatory factor analysis model, we are getting a CFI of 0.945. The second is RMSEA, root mean square error of approximation. This is this value should be as close to as zero as possible. So for our model, this value is 0.05. Okay, and this also gives the confidence interval also ki what will be the value of this fit index in the whole population. So it is giving us a range of 0.053 to 0.064, and the actual value for the sample it is obtained is 0.058. So this RMSU value, as close this value gets to zero, that means the more the fitting model you have. Currently, the cutoff point for RMSEA is 0.07. If the value of RMSEA is greater than 0.07, then we don't consider that to be a good fitting model. Okay. So for CFI, the criteria is value should be greater than 0.9, and for RMSEA, the value should be less than 0.07. If these two indexes, if your model passes these two indexes, then let us go to the next stage. So as we can see that for our model and our data, we are getting a CFI of 0.945 and RMSE is 0.058. That means it is in the acceptable range and we can now go further. Okay. Now if we look at the graphical output, you can see that all these constructs, they have indicators. This is basically known as a construct, latent variable, factor. These are all interchangeable terms. Okay, construct, latent variable, factor. That's why sometimes it is also called as factor analysis, latent variable analysis, classic construct theory. These are interchangeable new names, but they all refer to this same exercise, that is doing factor analysis and then ascertaining the reliability and validity of the scales used. So as you can see that we have supply chain alignment here, agility here, 8 items, adaptability here, 3 items, firm performance here, 4 items, competitive advantage, 3 items, trust, again, we have 4 items. So we want to see that whether this arrangement that we have made, that we are measuring supply chain alignment by asking these 4 questions, agility by 8 questions and so on, whether this is a valid and reliable instrument or a valid and reliable questionnaire or not. So for this, we conducted our confirmatory factor analysis. We loaded all the variables in the canvas, draw covariances between them, and then hit calculate. So first of all, we will go to this outer loadings. Okay.
So one question over here.
Yeah.
Can we go back to the say, diagram?
Yeah, please.
Sir, I just want to ask that why we have connected all these together, like
Okay, why we have connected all these together?
together, and why like competitive advantage is not connected to like we can see agility or something. Yeah,
Yeah, basically what we are trying to do here is when we are running confirmatory factor analysis, okay,
yeah,
we what we want to see is ki whether what is the degree of correlation between all these variables. Why?
okay,
Because as we saw in regression analysis, there was a thing called multicollinearity. Okay,
yes,
so for there, I discussed that for multicollinearity, we can use partial least square regression, group the variables into one factor and then run them. Okay. But
yes,
how we will judge the multicollinearity issue in what you say, SEM, when we are combining variables into another construct or a factor, and then that factor might have then again multicollinearity issue. है ना?
yes,
Because two, let us say, two concepts are there in a diagram which are more or less overlapping. They are just play of words. So in that case, the construct, the indicator will also exhibit multicollinearity, and when that indicator is jumbled up into a construct, that will also indicate multicollinearity. So
a construct can be related to another construct
yeah.
also, right?
So that
Yeah.
means we try to draw as many correlations as possible. I basically use a sequential, what you say, method. Amos does this very better because Amos has a plugin known as auto correlation. So you just click all the variables and you just click auto correlate before CFA and it does that optimally. Okay. This is a little bit shortcoming of smart PLS that I see, that it is not automatically correlating everything. You have to do it manually. For example, I basically use R for my most of the analysis. So this paper, if you see here, this is also actually analyzed using R only. So this is how the correlation, you can see all these values. These are done actually automatically by R as well as MOS. So Smart PLS is not doing this automatically. I don't know what's the reason they have not given us an auto feature.
Okay.
So I have done this manually. So I just connected it sequentially because everything gets connected to one another. So वो effect आ ही जाता है so that. Okay, so
Okay.
we need to first of all. Now this is the table. This is the correlation matrix. Okay. So I think 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All the 6 variables are here in this matrix. That means ki we have tried to connect all these variables correctly. Okay. Because we have 6 variables. 1, 2, 3, 4, 5, 6. And the matrix here also has 6. That means all the variables got connected correctly, and we have now a correlation matrix. So we can just clearly glance at the correlation matrix and we can see that none of these variables, the correlation between the variables is hitting the high area of 0.8, 0.9. We are getting highest correlation here is adaptability and agility 0.2, then firm performance and competitive advantage 0.3, 0.27, and this one is there because this is the diagonal and every variable correlates with itself perfectly, so that is ignored. Supply chain alignment and adaptability, so none of our correlations are in the very high zone, so that is a very good sign that we are not suffering from multicollinearity. Okay, now we will have to see the loadings. Okay, what are the factor loadings and what these loadings actually mean? Okay, what these loadings actually convey, what they mean, what are their what you say purpose, and how we interpret these loadings. Interpretation is very important. Now, in the diagram, if you see, and as we discussed earlier, we say that these are constructs, latent variables, or factors, and they are measured by indicators. And we first of all try to establish whether these indicators can reliably predict this underlying construct. So how do we do that? How do we ascertain or keep our foot down that these indicators are reliable and valid predictors of this underlying construct? So for this, we ran this CFA, and the purpose of this CFA was to obtain factor loadings. Okay. So this is our factor loadings. What these factor loadings basically indicate is they indicate how much this indicator alone contributes to explaining this construct of adaptability. For example, adaptability has three indicators. How much these indicators contribute towards explaining adaptability. So this is nothing if you just multiply it by, this is 0.7. If you just multiply 0.7 by 0.7, you will get the amount of variance that is being explained by this, what you say, one item in the whole construct. Okay. So this is how we interpret this factor loading. For example, this is 0.8. So 0.8 into 0.8, that will explain that means this item, second item alone explains this much variance in the underlying variable. And the cutoff value for CBSEM is 0.5. Okay, these loadings should be greater than 0.5. It is, if they are falling below 0.5, that means the model is not fitting very accurately. However, it is showing 0.6 as what you say, red, because smart PLS initially it was made for PLSM only, and in PLSM we consider a higher threshold. We consider their 0.7 as a good loading. So it is, that's why it is flagging 0.6 as not good loading. But in CBSEM, the threshold is 0.5. All your factor loadings should be greater than 0.5. Next very important thing is in this final result section, outer loadings, we first of all look at this matrix standardized. These are the standardized estimates. As we saw in the case of regression, that means these values fluctuate between -1 and +1 only. So gives us a very good relative comparison of how much important each of these indicators are towards predicting our underlying construct. So these loadings should be around, each other very much only. For example, you can see 6.5, 6.3, 6.1, 6.6. That means the importance of the questions is more or less the same. But if the loadings are, let us say, fluctuating a lot, then that means ki one question is very less important, other question is more important. And for example, here you can see two loadings are 0.6, two are 0.8. That means these two questions were considered more important by the respondents. These were not. So this is basically how you get a very good idea of what is the contribution of each of these items in explaining the underlying construct. And that contribution is basically known as factor loading. And for a contribution to be significant, the factor loading should be at least greater than 0.5 in case of CBSEM. Now in this outer loading section, if we go to this first option, list unstandardized, you can see that we have t value and p value also. This is nothing, this is same as regression also, because since we are doing some kind of prediction here, so we will get a estimate, then the standard error, and if we divide the estimate by the standard error, we will get the t value and the p value. So we can see here that, for example, we can see firm performance. Now I have, what you say, arranged it alphabetically. You can see adaptability. It has three items: 81, 82, 83. These were the unstandardized coefficients. And you can see that all the factor loadings were, what you say, significant. Okay. Then in the second construct, you can see that it has taken two of these loadings as, what you say, constants, because in CBSEM what happens is it takes one or the two indicators here in every construct as, what you say, constant, and set its value to 1. But don't worry about it. If you look at the standardized estimate, you can see that there is no 1, because in case of standardized, the mean is 1 and the mean is 0 and the standard deviation is 1. So that's why we report the standardized loadings only. We use the unstandardized loadings just to see whether all the loadings are statistically significant or not. Okay. So as you can see, all these loadings, they are getting a statistically significant result. In every construct, you see there is one which is showing NA because it is restricted to 1. This is one of the assumptions of how the model is estimated that you have to restrict one of the items to one. And this is the standardized matrix that we basically report. So what we do is we will just copy it and open our what you say Word document. Okay, we'll just go to a new page, paste. So this is our what you say the factor matrix. And this is the same thing that you saw in the paper. These values which are you are seeing here, factor loading standardized, which I have written. Okay, these are the same values which are obtained from this outer loading matrix standardized. Everything clear here? How we calculated what are latent variables, why we use confirmatory factor analysis, what are factor loadings, everything clear? Okay. Now let us jump to the next step regarding validity and reliability. I was saying this term again and again when using what you say this SEM and confirmatory factor analysis, that is validity and reliability. Now, what is validity and reliability? Very simply explained, validity means we are using these 3 questions to measure adaptability and these 8 questions to measure agility. Validity means are these questions actually representative of agility or adaptability? Do these questions actually serve the purpose of asking people? So how do we ascertain that? The one thing is that this factor loading should be close to one another. That means all these questions are trying to talk about the underlying issue, that is agility or adaptability. That is one way of seeing it. However, we can summarize these loadings into some what you say matrices which are easy to identify and set a what you say threshold for. So for this we go to this quality criteria model fit. Model fit, you can see we had our RMSE and CFA value, and below that there is one thing called construct reliability and validity. Let us click that. Okay. Now in construct validity and reliability, using that factor loading, we have calculated certain matrices here. That is composite reliability, rho C, and average variance extracted. Okay. These two things have been estimated here from the factor loadings, and that is this standardized factor loadings. Okay. So if we go back again to this quality criteria, construct reliability and validity, first of all, we see Cronbach alpha standardized. Now, what is this Cronbach alpha? Cronbach alpha is nothing. It is a measure of internal consistency of a scale. Okay, scale, for example, that kind of measurement that we have done. We are using 8 items to measure a latent variable or a factor. So these 8 items basically constitute a scale. So it basically measures the internal consistency. Okay, that whether the responses are in the same direction or they are consistent or not. So for good reliability, Cronbach alpha should be greater than 0.7. It should be 0.7 or greater than 0.7. Okay. So as you can see, for all the constructs, we are getting Cronbach alpha adaptability 0.87, agility 0.842, competitive advantage 0.972, firm performance 0.741, supply chain alignment 0.855, and trust 0.893. So these are quite above the threshold. So we don't look at the standardized, we have to look at the standardized only. So these are above the 0.7 greater than equal to 0.7 threshold. So that means this one quality criteria of reliability has been passed. Now, another important thing is validity. Now, in this stage, what we are testing here is convergent validity. Convergent validity means that this structure that we have proposed, okay, that alignment is 4 items, agility is 8 items, whether this structure actually converges onto the data that we have supplied. So that is measured using 2 matrices, that is composite reliability, which is also known as rho C, and average variance extracted. Now there is a formula for that, and these 2 matrices are calculated from these standardized loadings only. Okay. So what are the quality criteria? Composite reliability should be greater than equal to zero point 0.7, and average variance extracted for CB-SEM should be greater than equal to zero point 0.4. So you can see that some people actually attributed this as zero point 0.5 also, but zero point 0.5 is for PLS-SEM. For CB-SEM, we can go low to zero point 0.4, provided that all the other indicators are also above the threshold. So we can see that we are just achieving this threshold of zero point 0.4 for these two construct. Rest composite reliability is also greater than equal to zero point 0.7. So that means the quality criteria is pretty acceptable for this model. Okay. Now the next validity that we want to examine is discriminant validity. See, in the previous regression example, we were talking about multicollinearity and we examined VIF, variance inflation factor. In case of SEM, where there are latent variables, we have to establish discriminant validity to avoid that problem of multicollinearity. And for that, we have a criteria known as Fornell-Larker criteria. This is the criteria that is basically used for CB-SEM. Heteromonotate ratio is largely employed for PLS-SEM, that if you are doing analysis via PLS-SEM, it is important that you report heteromonotate ratio. And if you are doing CB-SEM, you report Fornell-Larker criteria. So what does this Fornell-Larker criteria does is, it basically takes this correlation matrix, which we saw. This is the correlation matrix of all these, what you say, variables, and it erases the half side of this matrix. इस half side को ये erase कर देगा, one के नीचे वाला सारा side रखेगा, and what it will do is, at the top of every column, it will just put the square root of the average variance extracted for that construct. For example, adaptability, if we go to this construct reliability, we have an average variance extracted of 0.599. So this value here at the top basically is the square root of the average variance extracted for adaptability. These values are nothing but correlations which are same from this table. Okay. Then for agility, it is saying the square root of average variance extracted is 0.623. Again, the correlations are mentioned here, same from this table, as you can see. Then for competitive advantage, the square root of average variance extracted is 0.9. And similarly, for everything, it has reported the diagonal as square root of average variance extracted. Now, how we judge discriminant validity from this table? This is nothing, just the correlation table. And from this diagonal, it has erased everything above the diagonal. And on the diagonal where these ones are there, it has replaced these ones with the square root of the average variance extracted. And average variance extracted was calculated in this table. Okay. So how we judge discriminant validity from here? The top value, where we have replaced the one with the square root of the average variance extracted for every variable, this should be the greatest value in that particular column. For example, if we see this column adaptability, we can see that 0.7 is the highest value. Then when we come to agility, we see that 0.6, which is coming in front of agility, this is the highest value. Then we come to the third construct, competitive advantage, and we see that the 0.96 value, this is coming in front of competitive advantage. So every construct at the top of this diagonal should have the highest value. If the value is not highest, for example, this 641, for example, there is some bigger value here, then that means there is issue with discriminant validity, and that means constructs are trying to act as shadow copies of one another instead of being very, distinct constructs. They are not bringing anything new to the table. They are just inflating the R square of the model. So once again, I'll just repeat. We start with the correlation matrix. On the matrix, on the diagonal, these are ones because every variable correlates with itself perfectly. Then what we do is we erase the upper half of this matrix above these ones, and instead of 1, we basically copy the square root, we copy the average variance extracted, take its square root. For example, adaptability, average variance extracted is 0.599. We will just take its square root and put it here. And when we see that in this column, for all other variables, the highest value here is 0.744. Other values, bigger values are zero point 0.2, zero point 0.3, which are less. That means we have established discriminant validity using Forner-Larker criteria. Secondly, we are doing this for agility, competitive advantage, firm performance for every construct. Okay. So this is the first of all validity and reliability aspect of the covariance based SEM model. This is also known as a measurement model, okay? Because we are trying to first of all justify what what the measurement that we have used for these constructs or these latent variables or these factors. First of all, they are valid and reliable, and then only we will proceed towards the what you known as causal analysis. So now what we will do is we will just click here, edit, and we will now remove all these correlations. Okay, we will remove these paths, and now we will test the main model from which we will try to infer our causality, because now we have what you say established that our model, our measurement is valid as well as reliable. So now what we can do is we can remove these correlations, and now we can get to the main job of establishing causality.
Sir, I have a question. Some of the latent variables were earlier not connected. So, should we connect each and every one with one another, or we can skip also?
You can connect as many as possible, but if you see in the correlation matrix that we obtained, all the six variables were there. Okay, if any of the variable is missing, let us say you have six variables, and in the matrix, let us say you are only ending up with five variables. That means one or two variables are missing. Then in that case, you have to connect it manually. Okay, but if all the variables that are present they are showing up in the matrix, then that means the connection issue is sorted. So now let us connect these like we had in the study and try to, okay, so now let us just verify it. It is very important at this stage before you draw the model to get it analyzed, ascertain that all the connections and the direction of the connections is correct. Okay, so we are just saying supply chain alignment, adaptability, agility. These are connecting to competitive advantage then connecting to firm performance, and then trust is again an independent variable which is affecting firm performance. Okay. So now in this model, we are trying to do the causal analysis, and in this model, there is also mediation. Means these independent variables are not directly impacting firm performance, but through another variable known as a mediator, which is competitive advantage. Okay, so we will be killing two birds with one stone. We will be seeing how to do causal analysis with CBSEM, as well as how to take it further and use it for testing mediation also. So as you can see, this is our mediator, competitive advantage. These are our independent variables: trust, alignment, adaptability, agility, and firm performance is our dependent variable. Now, as you can see, everything is set up correctly. Since competitive advantage here is the first stage dependent variable, it has an error term. Similarly, firm performance is also a dependent variable, so it has also an error term. So I think everything is set up correctly. All the arrows are set up correctly. These effects are coming here, then this is going here, trust is coming here. Okay. So now let us run this model by clicking calculate. Okay. And there are two options here, basic and CBSEM bootstrapping. We will be using the second option, CBSEM bootstrapping. Why? Because we have a mediation here. Okay. We are not connecting these independent variables directly to the dependent variable. We have a mediator. First of all, these affect this, and then this affect this. In order to test mediation and to calculate the significance or the statistical significance of mediation effects, we need to do bootstrapping. Okay. So we will just click CBSEM bootstrapping. This time we'll use this algorithm, CBSEM bootstrapping. Okay. And CBSM, all the things they are same. In this bootstrapping setup, it is showing how many bootstrap samples we will require. So we will just put it 1000 and random seed. We can change the seed also. If you change the seed, put a random seed, it might give slightly different values from the second or the third digit of the decimal. So it is recommended that you fix the seed. Okay. And you just seed is basically a starting point from which computer starts to generate random numbers, and bootstrapping is a randomization process through which we generate a distribution from the sample data so that we can generate statistical significant values. Because this competitive advantage, this mediation variable, the mediation coefficient is not normally distributed, so we cannot just divide it by the standard error, and we cannot have a standard error in that case, because standard error is there when we have a distribution. So you have to construct a distribution, and for constructing that distribution, we do a bootstrapping, and we will be taking 1000 samples by replacement from the main sample to do this thing. So I'll just set it to 1000 and just click do parallel processing because it will make this faster. And don't try to do this on a laptop which is not getting cooled properly, because this will heat up the computer very fast, this bootstrapping process. So just click start calculate. It will take a little bit of time, as you can see. It will take around a minute to run this 1000 samples. It is basically constructing a sampling distribution of 1000 samples, which are derived from sampling by replacement from the main sample of 379 data. So this is how bootstrapping works. And it is a very effective technique to generate significance values for non-parametric tests. Any estimate which becomes non-parametric, which in this case is our mediation coefficient. So in this case, we'll do bootstrapping. Either way, if you are testing mediation using regression analysis or PLSM or CBSM, whenever mediation is there, you have to run bootstrapping. Okay, why it failed? It's showing it failed, but is actually calculated. Strange. It was showing that it was a beta version, so I think they have not worked out the kinks correctly. Okay. Nevertheless, let us now start the interpretation of this model. Now we have validated all these constructs. Now we are interested in these paths. Okay. So we will go to this section in final result that says path coefficients. Okay. And it is saying standardized. So we will click this option. And then we can see all these paths are there. And we are seeing the original bootstrapped sample mean. And if you divide the bootstrap sample mean by the standard deviation, we get the t value and the p value. So you can see all the paths are more or less significant, with trust to firm performance being the weakest. And let us others are more or less very powerful. This is the weakest, but still it is significant. Okay. This is the what you say path coefficients of all these models. And these are the confidence intervals, same thing. Okay. Now there are indirect effects also. What is indirect effect? If we look at this graphical point, you can see alignment can affect firm performance, but it has to go through competitive advantage. Similarly, adaptability can affect firm performance, but it has to go through competitive advantage. Similarly, agility also. So what this indirect effects basically tells us whether these indirect relationships also hold true or not. And for that only we did bootstrapping. So as you can see, adaptability, competitive advantage, and firm performance. If you study this causal path, you can see that the t value is greater than plus minus 1.96 and the p value is less than 0.05. That means this path, this indirect path is significant. Similarly, if we again see specific indirect effects, standardized, then again you can see agility, competitive advantage, firm performance. This is also significant, and supply chain alignment to firm performance via competitive advantage. This is also significant. And if we compare all these standardized coefficients, we can see that most powerful is adaptability, followed by alignment, and lastly agility. And you can see that in the coefficients as well as the p-values. The lesser the p-value, more the powerful the effect of the coefficient is, and that is also reflected in the value of the coefficient also. Okay, and then these are the total effects. That means every path in the model and its statistical significance. So we can see that the weakest path is here agility to firm performance. Okay, and these are our individual paths in the model. And lastly, but I am missing one thing in CBSEM here in the Smart PLSS compared to MOS, and that is there is no fit index for the causal model. I'm not seeing it. I don't know why it is. But nevertheless, this is how we evaluate a SEM model. First of all, we run the measurement model in which we co-vary all the variables, calculate the standard loadings, see the Cronbach alpha, composite reliability, and average variance extracted. Cronbach alpha and composite reliability should be greater than equal to 0.7, and average variance extracted should be greater than equal to 0.4. And if all these construct pass these what you say stage, then we can move further. Also, the loadings that are achieved by all these items, standardized loadings. If you see that any item is achieving very low loading, or the loading is going less than 0.7, then what the solution there is that we delete that item from the model. And this is the main purpose of factor analysis, that we try to ascertain which items are valid and reliable and which items are not. So if any item is getting a factor loading of less than 0.5 in case of CBSEM and 0.7 in case of PLSM, then we just simply drop that item, and dropping that item will improve your Cronbach alpha as well as average variance extracted and composite reliability also. Okay, so this is the final what you say analysis of the model. We started with this framework, and then we started with this framework and then we try to evaluate from our collected data that whether this theory that we are trying to develop, whether this fits the data. And first of all, in the measurement model, we saw that we are all these constructs and the items that we have used, they are fit perfectly. And secondly, then when we run this model for the causal effects, we can see that all the path coefficients are getting very good values, and the p-values are highly significant, path coefficients are also very good, and the indirect effects are also significant. That means our model is fitting the theory. So this is how we use the application of CBSEM to test first of all the measurement structure, that the questionnaire or the scales we have developed, whether they are valid and reliable, and secondly we can also test the relationship of all this. Now we can do this with linear regression also. Instead of entering these variables as what you say latent variables, we can just put the summated scores and then draw a linear regression diagram like this and get the same result. Okay, the thing is that for this we have to first we have to validate the questionnaire also in the same way, that we have to run the measurement model. That is the first phase, by correlating all these things, calculating the factor loadings, composite reliability, average variance extracted, and after this, if when we are sufficient that no items need to be deleted from this, then we calculate the composite score, then use that composite score as a regression model. But we can do this once in SEM also. We just remove the correlations and we add the specific paths and then run the bootstrapping analysis also. So, any doubts in the causal path or the second stage of the CBSM analysis? Any doubts? Any clarifications that you may seek?
So, as far as what I have understood is, just as we have three indirect paths,
Hmm.
yeah, Steve. So, if any of the indirect path do not have significant value,
Hmm.
we can write in our analysis that the two paths can be followed to achieve the desired result.
Yes, yes,
Like, है ना? And this path can be omitted
yes,
because the
yes.
study has been done.
Basically, we are trying to test the theory from
Find
the
out.
observed data. है ना?
Yes,
So we
yes,
have theorized that this alignment will affect competitive advantage and then this will
yes,
affect firm performance. But let us say
yes.
this one of the path fails, then we say that the observed data and the theory में हमारा ये mismatch है and other
Yes,
tools are matching. So
true.
this is how we report this kind of
Yes,
result. Okay.
right.
So, what do we need to report when it comes to structural equation modeling? First of all, that factor analysis table. This table of factor analysis we have to report, and we have to mention below that all the constructs have factor loadings in the items greater than zero point 0.5 in case of
That I
CB7.
have understood, but in case, because we will do it for the first time,
Mhm.
after doing everything, we get indirect effect and see that one particular direction is not showing what I have to do. So I concluded in this way I can report the
Okay.
analysis. So one thing
Mhm.
which is a childish question after moving too much ahead, I'm asking what is the difference between PLS SEM and CB SEM?
PLS SEM uses partial least square regression as its estimator, whereas this CBSM uses maximum likelihood as its estimator. Okay. Mainly, this is the only mathematical difference. Both of them work on the same logic that they try to create latent variables from indicators, and then they try to validate those indicators, and from those validated indicators, they try to estimate paths, causal paths that we have tried to test with the observed data.
Okay, means there will be no big error if we choose any of the model.
Yeah,
If
no,
we have several
there
independent
won't be any
variables.
big difference. The only difference is that you might get certain changes in digits after second or third places of decimal, and that is
Okay.
basically mainly due to the seed, that is the random number seed that the computer is using to start the analysis. So that is mainly due to that. But if the data collected is identical, the model is identical,
Result
there is
is
no difference.
okay.
Estimates, you will not get any difference. Okay, for example, it might be 0.57 in case of CBSM, in case of PLS, it might be 0.58. But the thing is, 0.57, if you round it off, it will become 1. And if you are rounding out 0.58, then it is also becoming 1. So there is not much big difference. But the errors usually creeps in after 2 3 places of decimal. For up to 2 places of decimal, there is no significant difference in the estimation done by these two models. Okay.
We have to measure the result after three places of decimals.
Mhm.
Okay, we need not to go much more.
And
We
yeah,
or
you
we
can
have
report
to
just up to 3 places of decimal. Up to
yeah.
3 places of decimal is sufficient, and that is the acceptable convention that APA suggests for reporting in all the research papers. Okay, 3 places of decimals is actually reported. I have you if you see my reporting here in this paper, it is all 3 places of decimal only, nothing more, nothing less. As figure as well as in diagrams, both we have just reported 3 places of decimal. You can see everything. Okay. So that is the convention that we report 3 places of decimal. Any other queries regarding CBSEM? Any question regarding any of the two phases of CBSEM, the confirmatory factor analysis as well as the final causal testing? Any doubts?
So one thing I want to ask you that while doing this, our latent has not become blue in color. So why is it so? Because I think as soon as they start working, they are converted into blue.
Oh, this is why you are saying this diagram is not turning blue.
Yes,
Uh,
the latent variables. Yes.
Actually, that is dependent on the color scheme. What color scheme we have followed. Okay. Actually, I'm using this on Mac. I'm not using this on Windows. So there might be slight differences in color scheme, but you can change the color scheme to, for example, this. Yes, you can change the coloring here by
No,
clicking.
no. So I just want to know whether it is compulsory that these should be, converted into blue since, I read it somewhere that as soon as they start working, they will be converted as a blue.
That was necessary in Smart PLS 3. Okay. Since this new
Fine.
version of Smart PLS 4, this is not necessary that this should be converted into what you say blue. The only thing is that there should not be any stray variables in your canvas. Means the variable should be connected somehow to another variable, whether it's a correlation arrow or whether it's a what you say a causal arrow. Okay. There should
Fine.
if there is any stray variable, then it will error out when you try to put calculate. Okay. This is the main thing. And now since
Fine.
because now this PLS Smart PLS also has implemented CBSEM in the algorithm also, so that's why they have I think taken a little what you say soft stance on this whether this will turns blue or not, because in that case of PLSM, every item needs to have this causal arrow only. In that PLSM, we don't do that correlation analysis first. We do it with VIF only. But in case of CBSM, we do it as a measurement model by correlating everything, then estimating and calculating the discriminant validity. In case of PLSM, discriminant validity is using VIF as well as the heteromonotate ratio. So that's why they don't require that correlation phase. They just directly can test this structure, and when you connect all these things, they turn blue. That's why the color scheme of more Smart PLS3 used to do that.
Fine. Fine.
Any other questions? Any other questions, clarifications? Even if you have questions regarding your problem, how to implement this tool regarding your problem, you can also ask. We have time. We have 8 minutes.
Good evening, sir.
Good evening.
Sir, I want to know this key so basic differences
Hello.
the
Can you
sir
please write your question? I'm not able to hear
CBSM
your
and
voice.
regression analysis.
Can you please write your question? I am not able to hear your voice.
Yes, sir. There is a problem.
Hello. Please, can you type your question in the chat box? I'm not able to hear your voice.
I am writing the question.
Thank you.
Okay, sir. I'm
In the meanwhile, any other question? In the meanwhile, I get the written question from in the chat. Anybody wants to ask a quick question?
Sir, in case of BT setup, you have set up one some number as 1,000. So why is it so, sir?
That is known as the
Less than
boots.
1,000.
That is known as the number of samples that will be drawn in the bootstrapping stage. Now, as I said earlier, we have this indirect path here. Okay. So, जब हमने regression वाला example देखा था, what we saw is that whenever there is independent and dependent variable, we have a coefficient, and for that coefficient, we also have a standard error. And when we divide the coefficient by standard error, we get the t value. And from that t value, we judge where the coefficient is significant or not. When it comes to indirect
Yes,
effects, when it comes to indirect effects, what happens is, if we want to see whether supply chain alignment affects firm performance indirectly via competitive advantage, what happens is you have to multiply the alignment to competitive advantage coefficient with the competitive advantage to firm performance coefficient. Now, when you multiply these two coefficients, from where will the standard error come from? Because the data, this is not calculated from the data, this is two coefficients which are multiplied. So what does this bootstrapping does is it will create 1000 similar models, calculate 1000 similar values of these two estimates. What how this will do, it will calculate this model 1000 times by drawing a sample of 397 randomly through replacement from the main sample, and this will be done 1000 times. And after that, it will construct a sampling distribution of this mediation value, and from that we can calculate the standard error, because the mean is there and there will be standard deviation, that is nothing but the standard error. You divide the mean by the standard error, you get the t value, and from that we can judge whether the indirect path is significant or not. That's why we did this bootstrapping, what you say, setup, so that we can estimate the significance of this indirect path. If there is no indirect path involved in your structural equation model, then you can just simply go to this basic CBSEM algorithm and start. But if there is indirect path involved, where their causality is transmitted through some other mediating variable to the dependent variable, then in that case you will have to set up this bootstrapping setup and set it at 1000 samples. I set it at 1000 because it will be quicker. Usually for papers and for studies, I usually set this to 5000, because the more, the bigger the sample, the less you can thus there's a chance to commit the errors, and more there is a chance that the underlying trend, it becomes, becomes very clearly dominating, and you can see that. Okay, so that's why we set up here is 1000. I was in a hurry because I want else काफी time lag jata. So if you are not in a hurry, you are doing this for your own study, set this as 5000, 8000, 10,000, how much you like. However, after 5000, there is diminishing returns. So 5000 is the ideal number you can set here.
Thank you, sir.
Okay. Okay, what is the difference in applying CBSEM and regression analysis? Okay, देखिए CBSEM and regression analysis both help us to infer causality in causal structures. CBSEM is used when we are working with latent variables. As we are seeing here, latent variable means the variable is not measured directly but measured through certain indicators. That means जब भी when we are doing a questionnaire based study in which you are asking people's opinions and you are trying to relate to constructs or abstract concepts together by asking questions, then in that case CBSEM is used. However, you can also use regression also, but initially you have to use CBSEM when questionnaire is involved, because you will have to first validate the constructs, जो कि हमने first stage में किया था, by correlating all these things, then calculating the factor loadings, and then calculating the average variance extracted. And then from after validating all these things, you can basically calculate the mean. Let us say calculate all the mean which I showed you earlier on the Excel sheet, and then use those scores as regression also. You can run the same model on regression also. There will be not much change in the results. But the thing is, we can with CBSEM we can do this in one go. We can validate the model as well as get the causality also worked out, and in the same vein we can also show the indicators also. Okay, but I see that the implementation of CBSEM still is not very foolproof for smart PLS, as this is showing in this what you say message in the dialogue, that this algorithm is in the beta stage. Beta stage matlab this is still is in testing phase, not fully implemented. So if you are actually interested in running CBSEM, I suggest wait a little bit before you try running CBSEM on smart PLS. Use MOS instead, because it is the bread and butter of CVSM for the last 1.5 decades, and it is very robust. There is no bugs in that program. So I guess CBSM for that, that is more fit. But other than that, CBSM and regression both can be used interchangeably. CBSM basically provides more convenience. so that we can test the validity and reliability of the scale as well as test the causal structure all in one go. So that is the thing. Secondly, CBSEM, as I said earlier, it uses a maximum likelihood algorithm to estimate the various model paths, whereas regression analysis uses just ordinary least square regression. Okay, so the complexity of the tool is very much, what you say, regression analysis is very simple and very easy to understand. You can even do it by hand, whereas CBSEM is a little bit more advanced and will require a use of computer. This regression analysis is that you can do this kind level of regression analysis by hand. No software is needed. But for CBSEM, you will be needing all these things because you will have to calculate the fit indexes and everything, all the loadings for each and every item, rerun the model again if something, it's not coming out correctly. So I think that is the main difference in applying between CBSEM and regression. Regression is basically used where we have observed variables directly available to us, and CBSEM is used where we don't have observed variables, but we have latent variables, and we need to first of all validate them, and then we can test the causal structure. So this is the main technical difference that we use in any study where latent variables, factors, scales, questionnaire, these are things are involved. You will always see the comment from reviewers or editors that this study should be done through CBSEM, because the thing is, factor analysis and confirmatory factor analysis you will always have to do when you are using scales. That is why SEM is preferred method of analysis when we are doing this type of analysis where we have scales. Other than that, if you are doing some kind of scientific research where everything is documented on ratio scales or interval scales and there is no abstract concepts are involved, then sure, you can use regression analysis directly with your independent variables trying to explain the dependent variable. And even this type of mediation analysis where there is mediator variable, this can also be perfectly done with regression analysis. Okay, SEM is more tool of for social sciences where abstract concepts are involved, and regression is a more tool suited for, what do you say, classical sciences where there is no abstraction in the measurement of the what do you say, concepts. Okay, there is here is it is abstraction. We are trying to measure this adaptability and we are trying to infer it, first of all, these three indicators, and then we have to see whether this inference is correct, and then only we can go to the next step of testing the model. So I hope this is the major technical and methodological difference that we follow when selecting making a choice for the tool that we want to implement. Any other questions?
Thank you, sir.
Welcome. Any other questions regarding CBSEM or regression or anything that we have discussed in this session? Any queries, any doubts, anything you want to be, revisit?